as before. Actually, it will include essentially all the SLE kappas. But I will see them from the point of view of statistical physics models. I've put the word quantum gravity in the title, and I hope to have 10 minutes to show you how one derives, between quotes, in the theoretical physics sense, the results for planes, random planes in the random curves in the plane from another system which is called, the same systems in quantum gravity, namely on random surfaces. I will address a specific problem here. I will address the problem of the, as an example, to look at the random geometry of the random sets. I'm going to look at the electrostatic problem of a fractal set, a connected conformal invariant fractal set. So, as an example here, I took the Brown motion. So it will be really what I'm going to consider in this talk, namely a fractal set, like a percolation cluster, or a Brown motion, or a self-reading walk, or a Potts cluster. And I will put that object at potential 0, put potential 1 far away, along some big circle, and look at the way the potential vanishes when you approach the boundary. That's a way to have access to the random geometry of the boundary, because in a way, knowing the way the potential vanishes tells you about the geometrical properties of the boundary itself also. So actually at the end I will have some information on the random geometry of the boundary, including in principle the Hausdorff dimension of the outer boundary. Because of course you heard already about the SLE kappa. You heard that there was a dimension for the SLE kappa and the dimension for the outer boundary. And when you do the electrostatics, the charge will be expelled. You imagine that this object, this body, is perfectly conducting. So it's everything is at potential 0, and all the charge will be expelled on the boundary at the outer boundary. So that's a way to address the geometrical properties of the outer boundary. Okay, so that's the. So of course I've put here Brown motion, but there will be any cluster, and just to, for instance, if you take a Potts cluster, for instance, this is a Q equals 3 Potts cluster. So that's a single Potts cluster, and you do the same. You charge it. You put at potential 0. So everything all the other components have been taken away. So that's a Fortuyn-Castelline cluster of the Q equals 3 Potts model, say. So everything has been taken out except for one connected component. Okay. So you put this at potential 0, and of course, if you look at so that will correspond to the boundary of this object, which is drawn here, will correspond to a certain SLE kappa, actually with, for people who ask, kappa here equal 24 over, what did I tell you? 3? And so that will correspond, the boundary here will correspond to a certain SLE kappa. And of course, when you charge it, 20, what's that? Yes, 20. No, that's not that. Okay, sorry. Sorry. Which one did I give you? You have it. Well, whatever. So I'm sorry. Okay, but I gave it to you. Well, whatever. So it corresponds to a certain SLE kappa with kappa greater than 4. And of course, as I mentioned, the outer boundary will be smaller, and the outer boundary will look like.
So sorry, this is a critical random cluster model for corresponding Q equals 3, right?
Right. So it looks something like that, right? So this is so the outer boundary, which is a fat curve, right? So which is a curve which is in the scaling limit, will have double points. That's a curve which is, huh? Oh, that's, thank you. Okay. Well, I was going to put 25 over 3, but it's not exactly that. So this is really a quite approximate image of a SLE kappa for kappa bigger than 4. So that curve in the scaling limit is going to have double points. It's going to touch itself. And then, of course, it expels an outer boundary, which is smoother. That was given to me by Amnon Aharoni. And here you have an outer boundary which is smoother, which will be given by another SLE kappa, with a kappa this time smaller than 4. And actually, by duality, it's, it's kappa prime equal 16, so you find kappa prime equal 10 over 3. So another SLE kappa. Okay. I'm not using the SLE kappas, of course. I'm using something else. But it boils down to this. So this is a simpler outer parameter, which will be, in the scaling limit, a simple curve. Okay, this was for motivating you. Now I have to go to the electrostatics. Of course, if you want a nice picture given to me by, actually, Sapoval in Paris, this is a percolation cluster where you have filled the inside of the cluster in green. You have emptied the outside of the cluster in blue, so you have a single component. And here you have all the boundary sites, so what we call the hull, so namely the SL is 6 this time. So the full boundary of the post cluster are all the small sites which are in light green here. And again, if you charge that, you are going to have potential 0 everywhere where you have green or light green. And the potential will vanish on the coast. And the question is, how does the potential, how does it vanish when you approach the boundary? Okay. But again, that's a way just to have some information about the boundary itself. Well, so the question is the following. So you look at so I take again as a model the Brown motion to be specific. And you look the way the potential H vanishes when you approach the boundary. So you split your boundary in a multifractal way, and you say that the potential is going to the power law with which it is going to vanish changes with the power law here alpha, changes from place to place along the coast. And so you are going to split your boundary into subfamilies F sub alpha, and you say that the boundary point belongs to the family F alpha if the local behavior, the potential is R to the alpha. And then the question you ask is, what is the Hausdorff dimension of the subset of the subset F alpha? The union of all the F alphas gives you reconstructs the boundary. So each subset has its own local its own Hausdorff dimension. So little f of alpha will be the Hausdorff dimension of the subset f of alpha. So that's just a splitting of the boundary into subsets. So the question is how to calculate f of alpha. So I'm sure I will be short in time. So I already give you the answer. Because so the answer will look like that. So this is in French, but by law I'm requested to give one transparent in French in each conference. So, well, that was the law they wanted to pass some years ago. I think it went in the oubliette, but, So anyway, so that's, again, the same thing, partition, f of alpha, the dimension. Actually, by Berling's theorem, alpha has to be bigger than 1/2 or equal to 1/2, because this is the most dangerous case where you have a needle, the potential near a needle. So alpha has to be bigger than 1/2. And the formula is given by this closed form. So at the end, so it's a function of alpha. But of course, it has also to depend on which object you look at, because it can be, there are many statistical models in the plane which are conformally invariant. So actually, it's going to depend on one parameter C, which is in conformal field theories, it's called the central charge of the CFT. And so we are going to see where it comes from. But essentially, that's the answer you are going to get. So of course, that's, I'm going to, if I have time, I will describe what it tells you about how this f of alpha behaves, but essentially we are going to get something like that. So you see there is a very simple parameter here. And when you move C, you are going to change so C equals 0, for instance, will correspond to the case of the Brown motion. It will also correspond to the case of self-running walks and also percolation. So all of these cases will boil down to one simple f of alpha. And if you take a C equal -2, for instance, you are going to get spanning trees. Actually, or actually the loop area is random walk, rather. Well, no, spanning trees, I mean, yes.
Yeah, just want to mention that this is exactly the same formula that you can prove for the multifractal boundary of SLE.
Right.
It's the same.
Yeah, of course.
Different method, but it's the same method.
Of course, I'm going to, I will tell you where you find the SLE inside. There is C, of course, will be a function of, C can be related to kappa. Well, so to derive that, I'm going to use this quantum gravity method. I should say that for people who are not feeling at ease with alpha, if you have a wedge, in a wedge, as your if suppose this is at potential 0 and you look at the way the potential vanishes when you approach the apex of the wedge. Potential vanishes like the distance to the apex to the pi over theta, where theta is the opening angle of the empty space. So that corresponds to alpha equal pi over theta. And since theta is between 0 and 2 pi, you see that alpha is going to have a range between 1/2 and infinity. So alpha is really, this parameter alpha I had before is like an equivalent electrostatic angle, okay, opening angle of the boundary when you approach a point. So by this relationship, of course, that's an equivalent angle because all of this boundary is winding about itself all the time. So, but we already see the range of alphas we can expect for f of alpha. And so I have to be a bit fast. And so instead of calculating f of alpha directly, you calculate the Legendre transform of f of alpha. You use the Kakutani representation. So you say that, see this is our cluster put at potential 0. So this is the potential 1 far away. And you represent the potential near the cluster by the probability that an auxiliary Brownian motion running from Z, point Z, towards the escape to the boundary at potential 1 before it has hit the boundary at potential 0. So I just use the Kakutani representation. So it means that the electrostatics will be really represented by auxiliary Brownian motions approaching the boundary. And there is something which everybody does in this kind of analysis. You look at you take the moments of the escape probabilities. So you do something like that. I'm a bit fast, but the ideas are simple. You suppose you're in a discrete setting here on the lattice, and you start at a few lattice spacings, and you ask from the boundary, and you ask so you represent your potential is over there. It's a probability of escape from an auxiliary Brownian motion. You take the nth moment, and this nth moment, if n is an integer, is going to be represented by a packet of n copies of a Brownian motion, which have to escape to far away without having hit the cluster. So the nth moment will be represented by these auxiliary Brownian motions. And you look at the way, so you sum over boundary points, and this is the first hit probability, if you wish. So you sum the nth moment of the first hit probability over the boundary points, and you look at the way this quantity by itself scales with, let's say, the size of your cluster. I call R the size of the cluster, right? I look at the large distance properties instead of the short distance properties. By scaling, of course, that's the same. So I look at the way this nth moment scales with the distance, the size, and that is going to scale with some exponent tau of n, depending on the number depending on the moment you have taken. Yes?
The problem, of course, is that you've got expected behavior and you
Yeah.
go to a typical behavior.
Yeah, of course, in the kind of theoretical physics the techniques I'm using, we assume that everything goes smoothly. So of course, when I sum over the boundary, I expect somehow it is performing the sum already. Otherwise, you should have to take the expectation value later about the shapes of the cluster. But in principle, it's done by just summing, right? But you control all of that, so it's not the idea. I want to use some.
So this is exactly the moments of the derivative Stefan was speaking about. Right?
Yes, right. Okay, it's well known, and for theorems about the Brownian motions, for instance, you can look at Loewner's paper a few years ago. It's well known that, or also to some of your papers, it's well known that f of alpha is going to be the Legendre transform of this function tau of n. So but essentially, it's a symmetric Legendre like the one of thermodynamics. So f of alpha plus tau, are just summing up to the mutual derivatives of each other. So each alpha is the derivative of tau, n is the derivative of f, and they sum up symmetrically. So just standard, formalism which you get in the scaling limit. So it means that if you know tau, you know f. Okay, now I just change slightly the setting, and there will be. It's actually not. Okay, so it's not actually not exactly the same. Here I have minus 2 of n, which is the decay behavior of this summed nth moment. And actually I have to change slightly the definition. It's not a probability really. It's almost the same. It's just a shift of exponent. The same thing, a packet avoiding the cluster. And I wrote it as a probability, but it's not a probability in general. It's really a partial function of a cluster being avoided by the n order packet. That is going to decay with r to the minus x here. And actually, if you relate it to the former tau, it's just a shift by 2. But it's just because, why do I do that? It's because I want to have a scaling exponent x here, which is a really scaling exponent of conformal operator. And that one I can compute by quantum gravity methods. So just up to a shift, a trivial shift, you have a scaling exponent which you have to calculate. Because up to now, it's just a change of problems. That's where quantum gravity come in. So I just rewrite the same problem. It's not a probability, it's really a partial function. So it's the way this setting decays with the size is minus xn. And now xn is going to be calculated as the image by some map u of another scaling dimension, delta, which this one comes from quantum gravity. So I have to tell you what is u and what is delta. So quantum gravity, between quotes, is just a nickname in physics, theoretical physics. It's two-dimensional quantum gravity. It really means putting the same problem on a random lattice of the type introduced by Gilles Schaeffer 2 days ago. So remember, he had these random lattices. He was defining them carefully with, labeling graphs or not, and so on, and showing the way you have to understand these planar vertices. So I just imagine the same planar lattices. You take them and you put your system now, exactly the same thing I was looking at, on those planar lattices, instead of putting them on a regular lattice, like the hexagonal lattice of this morning or the square lattice, whatever. Okay? So you ask yourself the same questions. I don't tell you exactly how did you define it. Of course, you have to take big lattices. They have to be big, so actually what you do, you sum over lattices, you put your system on it, you sum over the lattices, and you go to a certain critical point because you look at generating functions where, on average, your lattice explodes. It becomes infinite. And you look at the scaling on that infinite lattice. Okay? So I should still mention the names. Actually, that was... This is old, in physics. It's the first ideas came from Kopolyakov in 81, actually. The idea of putting random statistical systems under a random lattice really was started by Kazakov, I would say, in 86. Then, so here I said that the averages of random lattices are annealed for people who know about the difference with Crunch. So that's really annealed average. Okay. So that was really, in the 80s. It was people were looking at random lattices as models of simple models of gravity or random surfaces. So the idea came to put statistical system on them. And in 88, you had this rather striking discovery by KPZ, who are Knizhnik, Polyakov, and Zamolodchikov. So 88, that any scaling dimension in a critical system in the plane is going to be the image of the scaling dimension of the same problem, the same operator, if you wish, on the random lattice. And so it's exactly the mapping I was using before. So you have a scaling dimension related to a kind of Hausdorff dimension in quantum gravity, and there is a mapping between those values. The two is just by convenience. Here I give you an example of what was predicted by these people. If you were taking what is named as pure gravity, meaning a pure random surface without anything, on it, and then you put some systems like a Brown motion, for instance, well, at least in this kind of approach, that the U function is going to be simply a quadratic map. You have seen, dimensions in Coulomb gas and so on. They are always quadratic, and of course, they are imaged by this kind of maps. So, for instance, you know which map you should have. For instance, for C equals 0, say. So you know actually the map in terms of C. So you know this map. You know that there is a pre-image somewhere in another system where, which gives you the scaling dimension of the same problem. So, yes?
They did that for C, for the Ising model, and then they conjectured
Yes, they gave in the first paper, you get the general formula for NEC. Yeah. Yeah. So I'm going to, so I assume this is true. Well, conjecture is never a word is never a word we never use. But apart from that, the statement, apart from that, yes. So I want to tell you, of course, so I want to tell you how you use this. You say the following. So I'm going to use that to calculate my x of n. In a brief, I mean, I take 3 minutes to do that. So I go back to a much simpler problem. Remember, what I want is a packet of walks avoiding a given cluster. Okay? So I start with something which is much simpler, which is a simple walk avoiding being in the upper half plane and diffusing on a disk. On a half disk, on an annulus, and you ask what is the probability that a walk starting from the Dirichlet boundary or nearby escape to a distance r that decays like r to the minus 1. We are in the half plane. We are not in quantum gravity. Okay. Now you ask same problem for a packet of walks. Okay, this one. So of course the probability of n walks being independent, scaling back, I mean diffusing away at distance r is r to the minus n. Of course, just independent. So this is trivial. But now you assume you are in quantum gravity. In quantum gravity, it's the same problem as this one, but now the upper plane will be a random disk, if you wish, a random lattice, half a random lattice. You are near the boundary of your random lattice. So this is u minus 1. So, of course, because this is a scaling dimension in the half plane, so it is the image by u of a scaling dimension in quantum gravity. So in quantum gravity, the scaling dimension is just the inverse image, u minus 1 of n. And u was a quadratic map, so u minus 1 has this form. I just gave you the example of c equals 0, right? So this is the inverse, the positive inverse function. So it means the scaling dimension will be complicated with a square root in it. And the reason for that is simply that these random walks get coupled by the fluctuations of the random lattice itself. So they get coupled, so get a non-trivial dimension. Because of the annealing, yes, because of the annealing. And now now a kind of key remark is the fact that, of course, our problem was not something like that. It was just a packet of walks avoiding a random cluster, not the boundary of the random surface. But the point is that it is additive, so you simply have, again, as an example, I took as a cluster, the black one here, as a Brown motion, so a self-reading walk. But I could have here put any cluster. And so now this packet has to avoid the cluster. Okay? But the key point is that the dimension you get in quantum gravity, so we are in quantum gravity, so you are near the boundary of the quantum disk. And the key point is that these dimensions are additive. Because you have to glue two pieces of random lattice which have to live together. You see, this is a problem of mutual avoidance, and the problem of mutual avoidance is linear in quantum gravity. It's not linear in the plane, but it's linear in quantum gravity. So that's a key remark. So you just add these things. I put u minus 1 of 2 because if this is a random walk, these are really, starting from a middle point, it's really like having two independent random walks. But otherwise, it's u minus 1 of something describing the cluster. And you add them. But of course, you are still in the half plane. The additivity works in the half quantum plane, not in the bulk. In the bulk, you have to do something else. And you have actually to sew the half plane to go back to a bulk. So you just sew it. And then you have another relationship telling you that the scaling dimension of this situation, a packet of walks avoiding a black cluster, is going to be given by the scaling dimension of this problem near the boundary. All of this is in quantum gravity, of course. And so the former boundary dimension, which is the sum of the two, plus a shift, and this shift is a cost to sew the problem. Now, if you want to make contact with SLE kappa, that's a good point here, because this is really gamma. 1 minus gamma is 4 over kappa. So you see, if you have an SLE kappa, the SLE would be the black object here. And this SLE is, here supposed to live in quantum gravity. So the gamma string you would have here would be related to kappa by this. So, but of course, up to now, you don't see it. And then, so now if you make a summary of the equations, you have, so this is the summary. You have the scaling dimension of, corresponding to the problem in the plane. So we will want to be in the plane. So a packet of Brownian motions, which is the nth moment of the potential, diffusing away from the cluster, is the image of the same thing in quantum gravity. So the same, this delta I have here. Delta itself is given by the boundary expanse in quantum gravity plus gamma strings. This is the same equation as here. Delta tilde is the sum of the u minus 1s. And then you plug, so actually there is a relationship between gamma and this one. So you put this here, you put this here, and you calculate and you get this structure. Well, because there is a cancellation somehow between this and that. So a simplification, say. So at the end, you get this kind of formula. And that formula is stable, so it's really always the same. So I just rewrite it here. And the structure is the following. It's the KPZ map acting on another scaling exponent, which is a mixing of the cluster frontier. This one in black is a trace. It's always one, but because there was this cancellation between gamma string and the part representing the cluster itself. And so it's always one. And then that is the inverse image, remember, of just a packet of quarks diffusing away from the boundary in the half plane. So this sends you from the half plane to quantum gravity. You fuse things with the cluster in quantum gravity, and you go back into the plane. And now, of course, U in general depends on, U itself depends on which cluster you looked at from the start. So it depends on if you were looking at a percussion cluster or a Q equals 3 parts cluster or whatever, or Brownian motion. So in general, you have this formula. Right here. Yeah, thanks. So U in general has this is stable, and U depends on which system you look at by this parameter gamma. And gamma itself is related to the central charge. And as I said, gamma is also related to the kappa of the SLE kappa. Well, and then, you scan your systems by varying gamma or C, and you find all the answers, right? And to be specific, so you remember I calculate tau. Tau of n was x of n minus 2, so you calculate it. You find a formula of this type for tau, which is the way the nth moment of the harmonic measure decays. And you Legendre transform it. So, of course, I have the parameter C describing which system I look at. And you Legendre transform it, and you find the formula I gave you at the beginning. Okay? So, of course, you could think, well, suppose you would have calculated that by another mean, like now with the SLE kappa, and you would have transformed your results into central charge. You would have written this. This would have been already conspicuous for theoretical physicists because 25 minus C, they know it appears in quantum gravity. But if you do the Legendre transform back, you see that, and that cannot escape because these square roots here of 20, this is typical of quantum gravity. So in a way, even if you had found this first by looking at the plane, you would have told your friends, and they would tell you, oh, you have here something which there is a trace of something happening in quantum gravity. And actually, I don't think I have much time to show you many things, but if you ask yourself, well, whatever. So it's already clear that there are square roots of 25 minus C and 1 minus C here. Now, suppose I draw this now, just to be more specific. So I take this as a result. I draw this for various values of C. So here. So all of these are f of alpha for various systems. So that's the answer to the electrostatic problem for various conformally invariant clusters. So C equals 0, as I said, corresponds to, is known to correspond to percolation, Brownian path, self-winning walks. And so there is a single curve which is describing the way the splitting of the outer boundary of a Brownian motion. The self-winning walk is a simple curve, so it is itself its outer boundary, and the outer boundary of the percussion cluster. So, of course, you always find the same f of alpha, and the same maximal value of f of alpha, which is 4/3, the one we heard about this morning, because of course the maximal value of f of alpha is the Hausdorff dimension of the outer boundary itself. The rest is just a decomposition in finer details. If you take C equal 1/2, this is the Ising cluster, so you have another curve. The interesting thing here is C equal 1, which is known as a hard boundary, which corresponds, of course, to kappa equal 4 in the SLA kappa. You know the famous point where the outer boundary and the boundary itself are identical in principle, where you have the duality between kappa less than 4 and kappa bigger than 4, which is going to start. So kappa equal 4 corresponds to C equal 1. And C equal 1 here corresponds to, if you take Potts clusters, corresponds to the Q equal 4 Potts model, where the transition becomes from second order, just starts to be first order. This is a hard boundary, so it means f of alpha cannot be higher. And the supremum of the f of alpha of all these curves is always smaller than 3/2. So it means that the maximum Hausdorff dimension for a simple conformally invariant curve, simple meaning self-avoiding curve, is 3/2. Of course, the polymer the polymer result is here due to Ninois a long time ago. And here you find it cannot be bigger than 3/2. And I wanted to finish with this duality. This dual, I might be a bit fast, but remember I spoke about some duality at the beginning between the outer boundary and the so I don't want to speak about typical angles, but I want to say the following. So remember you had take a curve, take a boundary which is so take the hull. So here I go back to an example of the Potts cluster. This was the set. This was a complete set of all the boundary points on the lattice. This set in the scaling limit is going to make a curve which is non-simple, which has double points. So this is what we usually call the hull. Well, a long time ago we used to call it the hull. So this is the full boundary. I told you that of course you have the outer, so it has a outer dimension dh. D hull. Now you have another one which is the outer boundary, also called the external perimeter, which is smoother, which is a simple curve, which has a dimension dep. Okay, and so the duality is the following one. You in the plane, as soon as dh is bigger than 3/2. Remember, 3/2 was the maximum value for a simple curve. So as soon as you are bigger than 3/2 on the right here, bigger than 3/2, you expel an outer boundary which has a smaller dimension dep, the outer boundary, given by this duality equation. And this doesn't depend on which model you are in, right? It no longer depends on the value of Q for a Potts model or whatever. And so, for instance, if you take percolation, this is 7/4, and you go to 4/3 here. So of course now, and that as you know, as we, for instance, so of course we knew that before because 7/4 was done a long time ago by Coulomb gas. 4/3 was done with Michael and Amnon Aharoni a few years ago, and well, it's not rigorous, but we find this kind of duality. But I wanted to insist on the fact that it is fairly general. And actually, you saw that in the equations written in the lecture before, because there was 1 plus 2 over kappa and 1 plus kappa over 8. And if you plug them, of course, they are going to satisfy that. So, but again, I found that from this quantum gravity approach. Okay, so okay.
Well, I think it's best to ask questions in private, if you don't mind. And let's thank all the speakers.